different rooms for different classes. So for this class, along with 104 and 105, we have Chem 237 running with graduate students from 11 a.m. to 1 p.m. Meaning if you're on campus and you have a chemistry-related question, please come in. Note not all of these people are RTAs, but Kyle, Coyote, and Cody, of course, are CSI person, and Bradley, Nicole, Johanna, Shabnam, Shu, Utom, and Franca, and Melissa have all taught this course, or are teaching it right now. So there's only a couple on there that haven't taught, but they taught general chemistry in addition to 100, 101 type courses, or 105. So if you're on campus, you have a chemistry-specific question, want to talk to your graduate student, please feel free to drop by. So I wanted to have that up there for you. In addition, I will be putting up a campus announcements, but I really just got the email a little while ago, so I didn't have time to post that. As far as our list, make sure that you are looking at Chapter 12 over the weekend. Remember, we do have the first couple sections in a video, should be reviewed, so that way we can focus more on the stuff that I'm not assuming is reviewed, which is intermediate courses for mixtures. We do have an open extra credit item that came through my email since we last met. It is up in campus announcements, but I just wanted to make sure that it was seen. I'm giving you 2 points extra credit towards your final grade in this course for completing these surveys. Please note, the names are not getting pulled until the end of the day of May 11th, meaning I won't get those points in until shortly before your final exam, but I'll have them in, hopefully, so I'll get the names on time before your final exam, because I want you to walk the door knowing what grade you have before you take that final. We know we have quiz 13, open on campus. It opened yesterday. Please don't get a lot of emails about that, and maybe it's just students who aren't coming to class. It is on campus. We don't have a quiz today in class, so that is a 60-minute quiz, 45 questions. Remember, it's only graded on completion, so if you have to guess, fine. If you don't quite finish it, that's okay. If you can send it to the study project or gauge your consent at the beginning of the semester, then we'll just be gauging your scale literacy growth throughout the semester. And I think I mentioned it last time, if you take 104, you're going to do it again at the beginning of the semester because it is a long-term research project. Exam 4 is on Thursday. It is cumulative for the semester. Last time you're going to lap them for most of you. 44 multiple choice questions, 60 minutes. You walk out with your booklet. What will get put up is a key that isn't just ABCDs. It's like answer was A, and this is why the answer was A, because you don't have a chance to, maybe there's DAs in discussion to go over it. So that key will get posted shortly after the exam's over, therefore you probably know your grade before I even get a chance to put it in. Final exam, exam 4 extra credit, don't forget about the scale site 2 activity. Cody sent you an email on the 2nd. If you're like, I don't know what you're talking about, I can't find this email, please send me an email as soon as possible because it just goes up at 9. And it isn't just a quick survey, it takes a little time if you want to earn those 5 extra credit points. Final exam for this class, the 15th, most students at 11 a.m. to 1 p.m. is this room. Cumulative for the semester, 2 booklets, each is cumulative for the semester, but asking questions from slightly different viewpoints. Common question is, are there any topics on the final exam that we have not covered? No. This booklet is chosen for a reason. We have covered everything that's on there, so there's no questions you should look at and say, I wasn't taught that. You say that, then, you missed something. In addition, as a usual Friday thing, I did open up the module for next week, but I just want to note, I did forget to change this due date here. It is changed now to the 7th. It was changed to Moodle right away, so that reminder is still up there. And we reminder for exam 4 itself, for Moodle exam 4, and then for the last day of instruction being Thursday the 11th, meaning if you have discussion on Friday the 12th, that is the study day, you do not have discussion. We also don't have lecture as well. I get yelled at by the dean if I did that. Any questions? No questions or stupid questions that we have for classes. Good? Okay. We're going to kind of pick up where we left off, so we get all this out of the way. Don't forget to do it later. We were talking about polarity. We had a definition. Oops, sorry. Where was our definition? In number 10 on page 288, just to remind ourselves, dipole moment tells you something is polar. So we have an equation for that, we're not using the equation. So simply a polar molecule has a dipole moment or an uneven distribution of electron density, whereas a nonpolar molecule, number 11, where we're technically starting, has an even distribution of electron density, and they ask us for the polarity of methane, which I have up on the center screen. We do have polar bonds, because carbon is one negative, one side is positive. All the electrons are getting pulled in one general direction. Yes, they're getting pulled inside, but we are the observers from the outside, so it is nonpolar and it has no dipole moment. Therefore, we have answer to 11A. Can molecules be polar if they contain polar covalent bonds? Can they be nonpolar if they contain polar covalent bonds? Yes. Methane has polar covalent bonds, however, it is nonpolar. All of our dipoles are canceling out. Any questions before we go further? So number 12 gives you a little procedure. You can, of course, do things differently, but we do need to have the Lewis dot structure either drawn out or maybe envisioned in your head, because that way we will see if we have a disruption in this canceling out process. We do need to think about geometry, which is why for number 2 it says in terms of bond angle and the shape of the molecule, you don't actually have to have the shape name in your head, but you do have to have the general shape in your head or drawn out. Assign the polarity to the bonds. Bonds are either nonpolar, homonuclear, two atoms of the same element bound to each other, or polar, heteronuclear, two atoms of different elements bound to each other. The direction of the bond moment, or the arrow, is assigned using electronegativity trend. We always draw the arrow towards the more electronegative element and from the less electronegative element. So that's why our arrows are going from hydrogen to carbon. Assign polarity to the molecule. If we have an even distribution of electron density, or in other words, the polar bonds cancel out, if you know about vector addition, you can use that, then it's a nonpolar molecule like our methane. If we have an uneven distribution of electron density, meaning not all the polar bonds cancel out, then we have a polar molecule. And we usually then assign the direction of the dipole moment for our polar molecule, meaning we could draw one dipole arrow for the whole molecule. For this, we couldn't do that because the electrons are always being pulled in. It's kind of hard to draw an arrow in. We would be going up, down, side, or side. Any questions before we look at some more molecules? So in number 13, it asks the polarity of several things. Carbon dioxide is one of these. Another example of something that has polar bonds, but is nonpolar. Because of its linear shape, the polar bonds are acting in opposite directions, and they're of exact equal strength because it's the same atoms bound to each other. If it would be something else on one side instead of an oxygen, then it would be a polar molecule because the two polar bonds wouldn't be equal strength. They would completely cancel out. If you use vector addition, one of them would be a little longer than the other, and it wouldn't cancel out if they were different atoms on the ends instead of two oxygens. They also ask about SO2. I'm not ignoring the CH2CO2. I have a slide for that. I wanted to have us think about SO2 right after the CO2. The way that we usually draw the Lewis structure, it looks like it's linear. But we have 3 electron groups, right? 1, 2, 3. It's really trigonoplanar as far as its base and bent. Because that lone pair on top of the sulfur repels the 2 oxygens downwards. And because we don't have a nice linear idea here, we would have, from our sulfur, 2 polar bonds pulling down, meaning the electrons are getting pulled in one general direction. We could draw a dipole arrow for the molecule. It is polar. Because of the shape not being linear, therefore the bonds, the polar bonds do not cancel out. I like to have that on the screen and then do that so you can see them side by side in a way. So geometry is a big deal, which is why this came after geometry. Good? Water is polar, we know that. We talked a little bit about the separation of charge in chapter 4, at least in that video at the beginning of chapter 4, right? We have a polar molecule because, again, the shape makes it so that the dipole arrows don't cancel out, or the strength of the dipole bonds, polar bonds, don't cancel out because those 2 lone pairs on top of the oxygen making it bent. And that's very a great advantage to water being polar. It makes it very versatile. So we do have a net dipole moment. We don't have to actually know the number. We just, again, I put that up there so we can recognize dipole moment is telling us that it's polar. We have still listed in number 13, CH2CO2, bless you. I have actually a string of molecules here, one of which being CH2Cl2, so we can see that although these are all tetrahedrals, the one in the middle being the one that was asked for, only 2 of these guys would be nonpolar, whereas 3 of them would be polar. Which two do you think are nonpolar? Anybody? Yes, because all the polar bonds would be the same strength. We already knew that our methane CH4 was nonpolar because we had 4 polar bonds, but they canceled out because they're all of the same strength, and that symmetry, that tetrahedral structure, makes it so they cancel out. Same thing would happen for CCl4, or carbon tetrachloride. Sure, there are different atoms on the outside than our CH4, but they're all the same. Meaning, a nice general rule that works a good amount of time, we'll say about 98% of the time. If not all of the, that's a bad D, go again, electron groups, grammar's not looking right to me. If not all of the electron groups are the same, it's more likely polar. Not all the electron groups are the same. It being the molecule. Are 3 in the middle. Yes, it has 4 electron groups, they get tetrahedral, but they're not the same. Yes, they're all atoms, but they're not the same atom. Which means you get different strengths of polar bonds. Meaning, they're not all going to cancel out. We have a dipole moment for the 3 in the middle. We actually have the dipole arrows also drawn for us. Hopefully it makes sense, since chlorine is much more electronegative than hydrogen or carbon. For this one here, the dipole arrow is going straight up. For this one here, it's kind of splitting between those 2 chlorines. And this one there, because there's 3 on one side, it's almost going to the side. Are there any questions? So we have to have this shape in mind. What does it matter if a molecule is polar or nonpolar? Hopefully you got a little bit out of that intermolecular forces lab. We have different attractive forces if we have a polar molecule than if we have a nonpolar molecule, which leads to observable macroscopic things that we can actually measure, like boiling points or melting points. I like to show this next slide because one thing I'd like to say, don't expect to ever see anything like that on an exam because it's very expensive to print in color. In addition, some people are colorblind, so that's unfair. But if you do see it on a website or a textbook, we have to understand that these are electrostatic potential maps. Here is our carbon dioxide for reference. So red, if we recall, is electron rich, blue is electron poor. So although it's a nonpolar molecule, electrostatically there are regions of more negative charge and a region of more positive charge, but it's nice and symmetrical, meaning the negative on one side is canceled out by the negative on the other side. Of the other 3, which ones are polar? Upper left, upper right, or lower right? Did I hear lower right? This one here? The negatives are right by each other, right? And the positives, the blues, you can't see the other blue, it's on the back side, are right by each other. Yes, that's a polar molecule. Of the other 2, is there another one that's polar? Upper left, we have 2 red balls, which are usually oxygens, but red going up as far as electrostatic map, and blue at the bottom. Those are 2 different molecules. This is 1 carbon in the middle. Those are 2 carbons, but they are all polar because of the arrangement of those attached terminal atoms. In the center, upper right, it's similar to the carbon dioxide. We don't have the electrons getting pulled in one general direction. We have 2 negative areas, 2 positive, but in a way they cancel out. Here, for the one down here, we could draw a dipole arrow going that way. So that one up there, we could draw a dipole arrow going up. For some students, seeing those images really kind of helps. I want to do one more, just because of this statement right here. What about our xenon tetrafluoride? If we recall, we had our 4 fluorines attached to xenon. I'm not going to be able to do this in a nice square planar. I'm just not the best at drawing them, which is why I'm not an organic chemist. I'd be really good at drawing these things if you're organic. But if you stop there, you wouldn't have used up all the valence electrons, right? So we have 2 pairs of valence electrons on the xenon, meaning not all the electron groups are the same. 4 of them are fluorine atoms, but 2 of them are lone pairs. However, it is nonpolar. Because one lone pair is on top, the other one is on the bottom, the effects of those not being terminal atoms canceled out. square plane, you have 4 polar bonds symmetrically arranged, meaning that the mean is this one cancel each other out, and the other two opposite cancel each other out. So this one is nonpolar. It is an exception to this, which is why I have to say about 98% of the time that works. I want you to see an exception. Any questions that come up? Do we recall that 2 single bonds is the same as a double bond? Right? Enthalpies were different, and the bond lengths were different. So let's actually explore this a little bit more when we start talking a little bit more deeper into our valence bond theory. We're on page 291. You can see at the top of the page, this is grouping 3 sections. We're just starting at the beginning. 10.3. How are single, double, and triple bonds represented in Lewis-Dot structure? Well, they're represented just with lines, right? So if we have a single bond, we have 2 electrons, we know we're sharing, and we have 1 line. If we have a double bond, we have 4 electrons, we have 2 lines. If we have a triple bond, we have 6 electrons, we have 3 lines. However, we already started hopefully getting you thinking about the fact that not all of our single bonds are the same. For one thing, just for the singles alone, there's different lengths and different bond enthalpies. So what's making these things different? Although we represented them the same, they're clearly not the same. So are all single bonds represented the same? Yes. They're not the same though. They don't have the same length, they don't have the same bond enthalpy or energy involved with breaking them. So I want to remind you about the table of bond lengths and the table of bond enthalpies in case you're like, what is she talking about? So we have those tables. So they're not the same. We're going to show you why they're not the same. So we have this image in number 20. This is a potential energy graph based on distance of separation between the nuclei. When you see those 2 spheres coming together, the nuclei is in the middle, but you think of those as atoms, right? Well, this is for hydrogen, so really there just is an s orbital around our nucleus. Notice as we start to bring the 2 orbitals together, therefore the atoms together, the potential energy dips. Remember, going to low energy is good, that's favorable, right? When we have the or the minimum of our potential energy, that's when we're making the bond, and the 2 hydrogen atoms are getting to be isoelectronic with helium. If we try to push them too close together, we get a sudden increase in the energy because we're getting those 2 nuclei, they're the center of those spheres, too close. And positives repel each other, so they don't want to be too close. We're getting beyond the optimal bond length. So we get an increase in the energy, which is not favorable. So valence bond theory is based on the overlapping of atomic orbitals in order to make a bond. Molecular orbital theory, the one we don't teach anymore because you forget, is based on the fact that when you make a bond, the atomic orbitals disappear, and what's created then is a molecular orbital. Just to give you an idea about the difference between the 2. I have another view, slightly different. Some students don't like graphs. So this is, I know there's what looks to be a bond there. It's just a bar, okay? We're going to bring our 2 hydrogen atoms closer to each other. Notice when they're somewhat close, we're getting a little bit of red, especially on the one on the left. You can see a little peak of red. Remember, red means electron rich, meaning the valence electron and single electron for hydrogen is starting to spend more time over there. As we get them even closer to each other and our orbitals start to merge, we get a lot of electron density red in the middle between the 2 nuclei. As we continue to get closer, that starts to grow. And notice we would be forming the bond right here. And this is a nice visual that if we kept pushing, we get those nuclei almost to try to interact. And they're both positive, they don't want to be by each other. So that hopefully will help you, if the graph didn't help, hopefully that will help you see what's going on. So we think of the formation of the hydrogen-hydrogen single bond as the overlap of 2 s orbitals. We call this s orbital overlap. So for our H single H in valence bond theory, s orbital overlap. Well, if you turn the page, what would you describe for the formation of a single bond in diatomic fluorine? What orbitals would be overlapping? We only have the s orbital in our hydrogen. Well, in our fluorine, if you look at the electron configuration, we would have a orbital in the 2p sublevel with only one electron in it. So we're going to have two p orbitals coming towards each other with that unpaired electron in each. When they merge, we'll have a pair of electrons being shared between the two. Therefore, for our fluorine, it's a different type of orbital that's interacting to make the bond. We call this p orbital overlap. So for our fluorine single bond, we're overlapping p orbitals. And hopefully this is helping you start to see as to why they have different lengths and different strengths, which is actually noted for you in part D. I'll put it up on the screen. So we have different bond enthalpies or bond dissociation energies and different bond lengths because we are interacting different orbitals to make the bonds. For valence bond theory, the bonds are formed through the sharing of electrons from overlapping atomic orbitals. Any questions? We haven't gotten the difference in a single and a double bond yet, but we'll get there. When we are doing this first interaction between orbitals to form a bond, usually a single bond, we actually call it something different in this theory. This comes up in number 21. We call these sigma bonds. So valence bond theory is based on modeling bonds with the sharing electron density between atoms as they overlap with atomic orbitals. We've said that. The model we have developed to this point is for a sigma bond. Covalent bonds formed by orbitals overlapping end-to-end or head-to-head. The easiest way to envision this is with the p orbitals. It's going that way, like two cars that are going to crash head-on. You can imagine if you had two p orbitals like this, they coming towards each other, they're not crashing head-on then. They're crashing side to side. And that's a different type of bond. We'll get there. We're going to show in this table just some visuals to help you understand. And I know for the s orbital overlap, we have already seen a couple visuals, but things are sometimes represented differently depending on the source you're looking at. So this is a slightly different representation. I think we saw an oval in that one that had the electrostatic maps. But again, I like this one because it's showing you somewhat where the bond came from. You have shape of S and shape of S merging. Therefore, for an S and a P, we should get a little bit of a sphere with maybe some peanut involved. I also like these particular set of images because for the p orbitals, it clearly shows how only one of the lobes is involved in the bonding. The other lobe, the orange one, hasn't changed shape at all. So when we would bring these two p's together right here, hopefully I can get this one drawn right this time. Every once in a while it's always like, can I get it right? Oh gosh, no. But we would have our bond right there, and this would be the leftover lobes. You can never get that quite right. It's like every couple of years I get it right. So compared to my bad scribble, let's look at what an author had put up. So there, that one's a little cleaner and neater, but I just wanted you to see that I'm not expecting you to draw that neat. If you draw it kind of funky, as long as it makes sense to you, that's okay. Any questions? No? Good. In 22, often the first bond formed is called a sigma bond. In this class and even the next class, every first line you draw in a Lewis structure is a sigma bond. You've got this head-on or end-to-end overlap of atomic orbitals. Therefore, we often equate one single bond to be one sigma bond. So therefore, what types of bonds are present in methane? There are 4 single bonds, therefore there are 4 sigma bonds. We'll see that there's a difference when we have double or triple bonds. If we're thinking about the actual orbitals that are going to overlap in our methanes, actually I want to put this on a new page. So I'm going to redraw our methane. about where the unpaired electron is in the hydrogen and where the unpaired electrons would be in the carbon. Well, for hydrogen, it's just 1s1, so we have an unpaired electron in a 1s sublevel, right? 1s orbital as well. In our carbon, if we're thinking about this, we have 1s2, 2s2, 2p2 to get to group 4, meaning we have unpaired electrons in the 2p sublevel. Well, if for each bond we have to overlap orbitals, we can understand for hydrogens we have 4 unpaired electrons in the s orbital. That's fine. To make 4 bonds in methane, which has been experimentally determined to be all the same length and all the same strength, how can we do that with only 2 unpaired electrons? We have to make 4 bonds. The theory doesn't always work perfectly, and when that happens, we have to change our theories to try to match nature, right? We don't change nature, we change our theories. So this is the place where the theory kind of started to fall apart a little bit. And we're getting into number 23. I don't always follow it word for word. Let's look at what's going to be going on. Sorry, we already went through that. I forgot to click. We saw the images. Very sorry about that. We're going to hopefully understand what hybridization is. It is the tweak to the theory to help us understand how, especially in methane and many other molecules, we can get a certain number of bonds that are, let's say, all equivalent, same length and same strength, from not enough orbitals. This is actually the mixing of atomic orbitals in an atom, usually the central atom, to generate a set of hybrid orbitals. Please note this is theory. This is our understanding of why nature is working a certain way. Meaning, if we recall that orbitals are simply wave functions, we blend together some wave functions. And what comes out is a set of hybrid wave functions, meaning they're kind of like resonance structures in a way. They're a blend of different wave functions. So we would expect to see sp, or atomic orbital overlap for our methane. We hopefully have seen that. We have s in the hydrogen, and we have p in the carbon. But we don't have enough unpaired electrons in the p. We need to get basically 4 unpaired electrons somehow. This is our complete orbital diagram. Nice note, some people use circles. I just did the p before. I didn't do the s, the 1s and the 2s. According to the theory, we know that we can excite electrons. That's not even theory. We can do that. If we give electrons some extra energy, we excite it up to either another higher energy level or a higher energy sublevel. So what we've done here is we've taken the 2s electron, it's paired up there, it's not paired here, so one of those guys would need a little extra energy to go up. Now we have 4 unpaired electrons. Does that help us though? If we use those orbitals to overlap with the hydrogen's s orbital, we would get 3 bonds that were the same through sp overlap and 1 bond that was different between ss overlap. So it doesn't still quite understand nature. It doesn't match nature yet. So the theory had to get extended. The next thought was, let's put it in a blender. Meaning in the quantum mechanical model, you put the wave functions into a mathematical blender basically, and what pops out are what we call hybrid orbitals or hybrid wave functions. If we do this using 1s and 3 p's, we'll end up getting 4, notice what it says right down there, sp3 hybridized. Which means our theory is telling us that hopefully nature is doing this, and we are hybridizing the orbitals in the carbon atom. And what we call that is sp3 hybridized. Do you have to know how to do that process to get the right answer? Like, what is the hybridization of this particular atom? No. Notice how we needed 4 bonds, meaning 4 electron groups. We had to get 4 orbitals, right? You always start at s. There's only 1 of those, right? Then you go to p. Well, we needed 3 of those to get to 4. 1 plus 3 is 4. We just never write the ones. So the sp3 is telling us the number of orbitals, which has to match the number of electron groups. Which also tells us that everything that is tetrahedral will be sp3 hybridized on that central atom. Because there'll be 4 electron groups. Everything that's trigonoplanar will have a different hybridization that's specific to the 3 electron groups. I think I might have another click that I forgot about. There we go. The definition of hybrid orbitals. So atomic orbitals obtained with 2 or more non-equivalent orbitals of the same atom combined in preparation for covalent bond formation. You don't look at beryllium dichloride. I did mention we saw the incomplete octets that we would get to them. Any questions before we do that? So for our beryllium dichloride, if you look at where beryllium is, it is in the second period, but the s block. So we'd be having an s orbital. From our chlorines, we know that they're at the end of the second period, but in the p block, meaning we would be using p orbitals. Sorry, this p orbital here. When we blend them together, we would get two sp hybridized orbitals, which is why beryllium will only have two bonds. This is only a certain number of orbitals that we can make. Also, beryllium will always be linear when it's bound to things, but it helps explain the incomplete octet. Any questions? Yes?
Can you just kind of like repeat that one more time?
From the beryllium, we're using an S, or I'm trying to think of different words maybe. We're using an S orbital, and we can see why, looking at where we're coming from. We're also then getting a P orbital from the chlorine. That's what's going to be overlapping. On the beryllium itself, sorry, let me do it the way that my brain wants to do it, but it's the way I told you don't have to do it. I'm trying to do it an easy way. For beryllium, we have 1s and we have 2s. Although we don't write the 2p, it's still present. What we do is excite to get a 1s, a 2s, and 2p. There's our two unpaired orbitals, which is how we get two sp hybridized orbitals from, each with an unpaired electron. And then because beryllium can only really have two hybridized orbitals is why we understand that beryllium will always have an incomplete octet. Those words help? Okay. Yes?
So when we just write SP, the S itself stands for 1s and 2s?
Well, it stands for S and NS orbital. A single S orbital. It doesn't have to be in a specific energy level.
It's just.
So we don't designate that this came from a 2s. Because what if we're working down far in the periodic table? We just say S and P.
Okay.
Notice we drop the.
S in general, wherever we happen to be.
We drop the energy level, yes. So the beryllium would be sp hybridized. They do give you a walkthrough, but however, really the important thing is the number of hybrid orbitals is equal to the number of pure atomic orbitals, but more importantly, it's equal to the number of electron groups. For our beryllium dichloride, I'm not going to do a Lewis structure, I'm just going to do a structural formula. We needed to add two things. So therefore, we use two orbitals to get to 2. But again, S1P1, that's telling you 2, 1 plus 1 is 2, gives you SP, meaning you don't have to do all this, which is why I was trying to avoid it, because then that gives students the impression you have to do that. Notice that covalent bonds are formed from the overlap of atomic orbitals with other atomic orbitals, like our diatomic hydrogen, overlap of hybrid orbitals with atomic orbitals, like in our methane, between the carbon and the hydrogens, or we can overlap two hybrid orbitals from different atoms. We have not yet seen that. Let's go through boron one quickly, and then we have something to do before we're done. So in our boron, after we excite, okay, we end up having a single s orbital without an electron, and then we have two p orbitals, a single s orbital with an electron, and then two p orbitals with electrons. Notice we excited one on the 2s up to the 2p. We blend those three together to get three equivalent hybrid orbitals, and since we use three original orbitals, it's sp2 hybridized. 1 plus 2 equals 3. Boron wants 3 bonds, especially in boron trifluoride. Again, boron often has an incomplete octet, and we're understanding this in our theory because of this. We're not saying that this is why. Theory does not dictate nature. This is just our understanding. But again, 1s, 2 p's tells us three electron groups. Next time we'll do a couple more complicated ones. We'll understand then when a double bond and a triple bond come into play. And then we have to do a couple things in chapter 12. Okay, so make sure to read that chapter 12 and watch that video. You're not walking out the door yet, though. You're doing evaluations today. So I am going to clean up which room this is, and my name, and what class it is. No, I'll wait until I'm out of here. He's not waiting until I'm out. Everybody just sees that I was trying to get out.